Right, let's start in 2 dimensions, a circle, and actually we already know the vector equation of a circle because it's very much the same as when we looked at the Argand diagram and used modulus and argument and things like that, and we saw a circle in the Argand diagram we could write as the modulus of z minus z0, where z0 was the centre, is equal to, well, that's essentially all this really is. That's a vector equation of the circle, where the centre would be v0, so that's the position vector, of course, of the centre, and the radius is r. If I was to break it into the components, so x minus x0 for the x component, y minus y0 for the y component, and find that magnitude, we can see clearly, yes, that's what we recognise to be the equation of a circle. Here we go. Cos squared plus sine squared equals 1. We know that. I could go r squared cos squared plus r squared sine squared is equal to r squared. Multiply everything by r squared. And straight away now we can see some parametrics here. X minus x0 would be r cos. Y minus y0 would be r sine. We created parametrics for our circle. But we're going to show that this represents a circle. Well, dot by itself, you'll notice we've got the vector dot itself, remembering that's the magnitude of the vector squared, but straight away I can do that. Well, that's the vector form of a circle. I got it straight away. So it does represent a circle, and from there I can read off and go, well, the centre is 2, negative 3, and the radius is 2 root 3. We're going to find the equation of the tangent to a circle. So here's my circle, there's the tangent. I want the vector equation of that tangent. If I was just to place r somewhere, some random point on that line, I could express that vector as r minus 3i minus 4j, head minus tail. But of course, that's the equation of any vector that goes through P, not necessarily the tangents. I need an additional piece of information to find the tangent, and that I'm going to use that theorem, the radius is perpendicular to the tangent. And so the position vector of P is 3i plus 4j. I know those vectors have to be perpendicular, radius perpendicular to tangent, and so now I could say, well, hang on, there's the equation of a line. Okay, it's still a vector equation, it's written in terms of vectors, not the format that we're used to seeing, but there it is. R minus 3i minus 4j dot 3i plus 4j is equal to 0. That would be a vector equation that represents that line. Well, what would the Cartesian equation then be? All right, well, let's do the dot product. So I'll break this first one up into its components. So group the I components together and the j components together. Multiply the i's together, multiply the j's together, and we can easily get the Cartesian equation of that line. Now we push the idea through to 3 dimensions, but again the vector equation doesn't change, but now instead of talking about a circle, we're talking about a sphere. Right? Remember, think of locus of a circle in 2 dimensions is a point that moves so it's always the same distance from the centre. Well, when you put that in 3 dimensions, sure, you get a circle on a particular plane, but of course you could go in any direction in that circle and it's still the same distance, and so we end up getting a sphere rather than a circle. But the centre will still be the v0 and the radius is still r. That hasn't changed. It now means, if I was to put it as magnitude of, then I've got a third component now. I've got a z component in there. There's the Cartesian equation. And as we've seen with a lot of our things going from 2 dimensions to 3 dimensions, it's essentially the same, but now we're adding in the third component. So a circle we'd normally see as x squared plus y squared equals the radius squared. We'll push it to 3 dimensions, you get x squared plus y squared plus z squared is equal to the radius squared. Now the parametrics, a little bit more involved here, but look at it closely. You'll notice the coefficient of cos and sine in the x and the y component is the same. So if I was to go x squared plus y squared, I would get r squared cos squared and then cos squared phi, r squared cos squared and sine squared phi, but cos squared plus sine squared is 1. So those two added together would be r squared cos squared, and now if you add it with the z squared, you're adding r squared sine squared, Oh, again you've got cos squared plus sine squared which equals 1. That gets us our parametrics for a sphere. Now let's look at some questions involving spheres. I've got two equations of spheres here. They're going to intersect. But if you've got two spheres intersecting, they'll intersect in a circle, because there'll be some plane that circle would sit on where they're intersecting. Well, we want to know what plane is that circle going to lie on. Now, the numbers were quite nice here for a simultaneous equation. We want to find where they intersect, solve them simultaneously. But nicely, you'll notice, oh, well, look, the x plus 2 squared, that's going to cancel, and the y plus 3 squared, that's going to cancel. So I end up with z plus 2 squared minus z minus 4 squared equals 9, and that comes down to be z equals 7 on 4. So that would be the equation of the plane that it lies on. So what's the centre and radius of that circle? Well, we now know z is 7 on 4. That's a constant 7 on 4. It's on that plane. Playing around with that, I can then get the equation of the circle that's sitting on that plane. X plus 2 squared plus y plus 3 squared is equal to 175 on 16. But be careful with something like this. It's very tempting to just go, oh, the centre is -2, -3. No, it's in 3 dimensions. Remember, z was a constant 7 on 4. So the centre is -2, -3, 7 on 4. And the radius, we do it the normal way. Find that square root, we get 5 root 7 on 4. If I just had that equation and I didn't have that restriction of z equals 7 on 4, it would not be describing a circle anymore. It would now be describing a cylinder. Because what we're saying is it's going to be a circle on every single plane, all parallel. If you think about it, well, that would be a cylinder. If you were to slice a cylinder down, you'd continually get different circles. Well, let's find where this sphere and that particular line intersect. Okay, again, how do we find the intersecting? We solve them simultaneously. So I'll substitute in the equation for r into that magnitude. Well, let's now tidy it up, group the components together. I get lambda I minus 2j plus 3 minus 2 lambda k. Let's find that modulus. Remember, we want to work out what lambda is. Let's create the quadratic. There it is. We can now find lambda. Ooh, well, it's not one of those ones that came out to be nice numbers, but it is what it is. 6 plus or minus the square root of 51 on 5. Okay, that means x is equal to 1 plus that. That'll give us 2 values of x. Y is going to be a constant 2, so that's okay. And z will be 3 minus that particular expression. It's a clumsy way of writing it, but remember the plus will go with the plus and the minus will go with the minus when we work out these 2 points. And it has to be 2 points. If you think about it, you've got a sphere and you've got a line coming through the sphere. It's like, imagine you threw an arrow at a ball or something. Unless, of course, it turned out to be a tangent, it's going to hit it, come through and pierce it in 2 spots. There's going to be 2 points we're looking for. Those 2 points then would be, well, first of all, I do the plus in each of those surds. I'll get 11 plus root 51 on 5, 2, 3 minus 2 root 51 on 5, and then if I do the minus in both of those, I get the other point. So V is the position vector of a point P on a sphere S with centre C and radius R. Who needs numbers, eh? So that I want to say modulus magnitude of V minus C is equal to R, and C is the position vector OC. Oh, don't prove this. The equation, it keeps going. Equation of the line L through the point P in the direction of the vector M is W equals V plus lambda M. All they're really saying is, hey, this is a vector equation of a line. If you think about it, it's going through the point V in the direction M. Find the value of lambda, or values, that correspond to the intersection of the line L. So again, we've got a line going through a sphere, giving your answers in terms of V, C and M. Of course, they didn't actually give us a diagram. Now, the first thing is to come up with a diagram to try and get my head around the problem. So I've got a sphere, and I've got this line, it's going through the sphere. Now, it'll have 2 points of intersection. We know one of those is V. Okay. The other one is W, because there's the equation of the line. W would be the other point on the line that I'm talking about. I know that they're going to be the same distance from the centre, so both of those are r. Okay. That means that not only what they told us, the magnitude of v minus c is equal to r, but the magnitude of w minus c must be equal to r as well. But w is v plus lambda m, and that equals r. I'm going to square both sides. Now when I square the left-hand side, I'm saying, well, the modulus squared is the same as that dot, the same thing. This now allows me to, for want of a better word, expand that out. But remember, we're actually using the dot product, not multiplication. I'll get v minus c dot v minus c to lambda v minus c dot m plus lambda squared m dot m is equal to r squared. Remember, we're trying to find lambda. Well, the ones that are going dot by themselves, I'm going to go back into the magnitude form and rewrite this so it looks like a quadratic. It's getting there. So that's, if I now subtract r squared from both sides, that's where I'm now at. Nicely, I got a common factor of lambda. I don't actually have to use a quadratic formula or anything like that for here. So either lambda is equal to 0 or lambda is equal to this expression. But they did say put it in terms of m, c and v, and that is in terms of m, c and v. I've done what they've asked me to do. But now, deduce that that line will be a tangent if and only if this is equal to 0, and interpret what you've just done geometrically. Well, if L is a tangent, we now know there's only one point of intersection. So what that means is W must actually be V. Remember we said W was any point on there, but if there's only one point of intersection, then W is now V. W though was V plus lambda m, so V plus lambda m is equal to V, which means lambda is equal to 0. Well, we got that solution, but if that's the only solution, it now means that the other one is 0 as well. So it means that is also equal to 0. And then, well, 2 is a constant, magnitude of m squared is a constant, and that just gives me the result that they're asking me to prove. But what does this now mean? Well, it means that the tangent is perpendicular to the radius, because dot product equaling 0 means those two things are perpendicular to each other. The same result we saw in 2 dimensions. Tangent is perpendicular to the radius. The same result happens in 3 dimensions as well. Alright, now that brings me to this question from the 2023 HSC question, and this really blew people's minds when it came up. So we have a sphere, but on that sphere we've got a spiral, and it's going around it 3 times. They've given us some initial conditions. They gave you a hint by using the diagram below. Whoa, what a diagram. It's got 2 different functions drawn on it. And considering the multiplication of those 2 functions, give a possible set of parametric equations for this curve. We know that in 2 dimensions, a basic circle will be in the form of x equals r cos, well, I'm using t rather than theta, but r cos t, y equals r sine t. We know that. That's in 2 dimensions. What happens as t increases? Well, the point will move anti-clockwise around the circle. So there's our circle. When t equals 0, I would be over here. If I substituted t equals pi on 2, I would now be up here. So I'm moving anti-clockwise around the circle. T equals pi, and around I would go. Now, if instead of a circle, we have a spiral going anti-clockwise, the parametrics now become this. Not r cos t, but rt cos t. There's a spiral. When t equals 0, because now I'm multiplying by t as well, I'm at the origin. But as t gets bigger, what we're essentially saying is that radius is getting bigger and bigger and bigger, and that's why it's creating a spiral. It's not a consistent radius. As you go, t increases, it goes around. So there's t equals 0. T equals pi on 2, I'd now be up here. T equals pi, I'm back on the x-axis again, but on the other side, and that's why it's going around anti-clockwise. It's getting there. Okay, back to our particular one though. Now, our 3D spiral will have that form. So the x and the y is still some function of t times the cosine some function of t, and the y will be some function of t, the sine. But the third parameter now is simply z, because we're moving along the z-axis. If you imagine compacting that spiral down so it's flat, we would still have that same 2D spiral. So the x and the y still have the same parametrics as the 2D spiral, but we're no longer flat, we're pulling that spiral out, and that's being controlled by the z value. So the simplest way of doing that is to say, well, I'll just make z equal t, and that will control the spiral. For this one, when t equals -3, I'm down here at the bottom. So I'm actually starting at t equals -3. T equals 0, I'm winding up, I'm now back on the xy plane. And then t equals 3, I'm up at the top. They gave us this hint saying that, well, if you knew that this was the form of the parametric, then I go, well, hang on, function x times g of x, these are the two functions you've given me. I know it's got to look like that, so, okay, there's my parametrics. Right, so I've used function x times g of x, that's going to be my x1. I know the y1, the function's saying the same, mind you, we've got negative there, and I'll explain that in a sec. And z, I'll just make t. I've got the parametrics. Why was it negative? Have a look at your spiral, what's happening. If you leave at -3 and start moving, you're actually moving to the negatives of the y. So I know I'm starting that way, so the y ended up having to be negative for that one. But just say you didn't know, now it comes to the theory I put there. Let's say you didn't happen to know what the parametric form is, what would you do? I'd still let z equal t, because it's still moving along the z-axis. Okay, so that's a sensible thing to do, but I'm moving from -3 to 3. They gave me the hint of considering function t times g of t, and there's function t times g of t. If I substitute in 0, so when it's on the xy plane, I end up at 3, and sure enough, if I look at that picture they gave me, yes, x was 3, so that must be controlling the x value. Now I know the equation of a sphere is x squared plus y squared plus z squared equals 9. So I'll substitute in what I've done. I've let z equal t, and I'm saying x is going to be this expression of them multiplied together. I end up with y is plus or minus. Which one is it? Well, that goes back to that same idea. I have a look at the picture and see what the spiral is actually doing. So when I leave 0, 0, -3, it goes negative. So it must be the negative case. There's the equation, parametrics. Let's just finish up looking at some just other pictures. A plane. But by the way, you don't have to know about the equation other than the coordinate planes and basic ones. But it will always be in this, because in 2 dimensions, a line, we know that's when we just have x to the power of 1 and y to the power of 1. So you get y equals mx plus b. If you push that through to 3 dimensions, it's no longer a line. You're pushing the line through, it becomes a plane. But the same idea, now you got z to the power of 1. So you get something x plus something y plus something z. Now, the one we saw before was z equals 7 on 4. Well, that's fine. It just happened for that one, a was 0, b was 0. And you got z is equal to 7 on 4. So that's a plane. Now let's look at some interesting ones. Again, you don't have to know this. There's a hemisphere. What is a hemisphere? Well, hemisphere is a semicircle that's been pushed into 3 dimensions. So it has the form of a semicircle. Depending on where the opening is, on which plane, and you'll see it's the z-axis that's controlling the sphere, so it's z equals, and then it'll be r squared minus the other ones squared. A paraboloid, again, this one's going along the z-axis, so z's controlling it, and that will be, instead of, in 2 dimensions we would have said y equals x squared. So now we're saying z equals x squared, but add the other pronumeral in, plus y squared. That would be a cone, by the way. I don't know, what would that be in 2 dimensions? Yeah.
Like a circle?
Yeah, you could think of it as a circle, but we're multiplying by this factor, so the radius is changing as we go up. A bit like that spiral, I suppose, that we were just talking about, same sort of thing. That's a hyperboloid. of one sheet. Now, we don't do this anymore because we don't look at conics, but the standard equation for a hyperbola would be, say, x squared minus y squared equals a constant. So in this case, we've got x squared minus z squared is equal to a constant, and the y happens to be positive. That's how we get one sheet, as opposed if the y was negative, we'd get two sheets. It's still, if you look at the boundary, it's still a hyperbola, but it's just one's on the inside of it and one's on the outside of it. And then there's the classic spiral, the one where the radius is not changing, the helix, which if you imagine compacting that down to 2 dimensions, that would just be a circle, but we're pulling along. So we get the parametrics of a circle, but now we've got Z controlling the spiral. Okay.